Okay, let us start our today group seminar. Today we have a talk on continuous normalizing flows, some method that is similar to the talk a week ago, also uses continuous time dynamics, solving ordinary differential equations, similar things, but this time the method is applied for the problem that I think is of the most importance for us as Bayesian people. This is the task of approximating the posterior distribution with some tractable manner and using it within Bayesian inference schemes. And the talk will be given by Alexandra, don't remember the name, our new federate in the group. Please.
Thank you for the introduction. My name is Alexandra, and today I'm going to talk about continuous normalizing flows. First of all, I'd like to remind you what we get from the previous seminar. We talk about Neural ODE and what is it about. We have a differential equation for Z, and our dynamics is a neural net. It has parameters theta and input Z and time. We have initial state for our differential equation, and we can find solution at some point t at some point capital T. But we couldn't do analytical integration, so we use some ODE solver to make it numerically. And it looks like this. The blue curve is a real solution, and the red curve is a solution of our ODE solver. And
not quite too stable.
Yes. For our neural ODE, Z of 0 is input and Z of capital T is output. And we want to train our system somehow, so we introduce some loss which depends on output of our neural ODE. And we want to know gradients of the loss with respect to parameters theta and with respect to the input.
Why do we need the derivative with respect to the input?
Because maybe input is not just data, but output of some other trainable system. Okay, and how can we get it? We can use traditional backpropagation and pass all derivatives through the all steps of our numerical integration. But this approach has a disadvantage. In the memory, because we need to store all values at each intermediate step of our numerical integration, and if we have a lot of steps, we will have to store a lot of values, and it may be too much in the terms of memory. To avoid it, we introduce a joint system in which A of t is the gradient of the loss with respect to Z at time t. And as we know from the previous seminar, A of t has the following dynamics. Also we know that the gradient of the loss with respect to parameters theta have the following dynamics. And how it can help us to train our model. First of all, we have Z at point 0, it's our input. We use this differential equation and ODE solver to get Z at time capital T. Then we can compute gradient of the loss with respect to the output of our neural ODE. Also, we know a gradient of the loss with respect to parameters theta at the time capital T, and it's always 0. So this is initial state for our ODE system, for this ODE system, and we solve it backward in time to get gradients of the loss with respect to parameters at time 0 and with respect to the input. Okay, this was a recap from the previous seminar. Now let's talk about normalizing flows. What is it? We have a random vector with distribution P0. And we have another vector which is a function of initial vector, and this function is smooth and invertible. Then we can write that integral in another way, that using change of variables theorem. And after that, we use the fact that determinant of the inverse matrix is inverse of determinant of the initial matrix. And looking at this more carefully, we can note that this is a density for Z1.
Don't you use here any assumptions on monotonicity or something?
On what?
About F, monotonicity.
It is invertible.
And that's enough.
Yes.
No?
Maybe it is a mistake, but I thought for the change of variable theorems it is enough to be invertible and smooth.
So, in one-dimensional case, monotonicity is necessary for the function to be invertible. But in multi-dimensional case, you just assume that the function is invertible.
You mean, by invertible, you mean one-to-one correspondence?
Yeah.
Oh, okay.
Okay, and we write it in terms of log probability and get this equation. And what it gives to us, we have a random vector and we transform it somehow. And we can compute how its density transformed to. Very good. Yes. Let's okay. Let's apply k invertible transformations on our random vector Z0, and we will get the following equation for its density transformation. And through this k invertible transformation, we transform our vector, and we know how its density transforms to. So the analogy is that distribution flows through a sequence of invertible transformations, and this is because this structure was named normalizing flow. Okay, any questions about it? Okay. And here we need to compute logarithm of determinant, and to compute determinant we need about cubic computations with respect to dimension of the matrix. And if we deal with high dimensional data, it may be too much. But we can put some restrictions on our function to make this Jacobian matrix to be a triangle. It will reduce number of computation, but it will make our transformation poor, and we couldn't be able to get complicated distributions at the end. Okay, continuous normalizing flow. Let's join two ideas, Neural ODE and normalizing flow. We have Neural ODE, and input goes from some distribution P0. We compute output using numerical integration, and we can compute a solution of Neural ODE because we have ODE and initial state. We also have initial state for density. And if we imagine that we have some dynamics for density, we will also able to compute density at the point capital T. And let's derive these dynamics together. First of all, we write the definition of derivative, and then let's look at z at point t plus epsilon. It is a solution of our ODE. Let's denote it as capital T epsilon, and look at this equation like a function of, like a transformation of z of t. If our function f is enough good, I'll explain later what it means, our solution is unique. And if it's so, our transformation of z at time t is invertible. Because if we stay at point t and goes to point t plus epsilon, we have unique solution. That means that we have unique trajectory, and if we want to go back, we need to use the same trajectory. So we will go at the same point from which we start. So this transformation is invertible. Okay, if it's invertible, we can use the equation which we derived for normalizing flows. Yes, it's just with determinant, and we put it into our equation for derivative. These terms kill each other, and we get only logarithm of determinant. And now let's see. Let's write our function t, capital T epsilon, using Taylor formula. And after that, let's differentiate it. We get identical matrix and Jacobian of f multiplied by epsilon plus usual O of epsilon. And
something wrong with dimensions here. You have a Jacobian, a huge matrix which is multiplied by just a number.
What's
epsilon?
Scalar. You can multiply matrix by scalars.
Yes. No, epsilon it's a scalar.
Yes.
And it is a matrix. We just multiply matrix on a scalar. Okay. And epsilon tends to 0, then this matrix tends to identical. And determinant tends to 1, logarithm tends to 0, and both these terms tends to 0. That means that we should use L'Hopital's rule, which says us that this limit is equals to limit of derivatives of these terms. So derivative of this term is 1, and of this is here. And let's use the following equation for derivative of logarithm of determinant of the matrix. It's equals to trace of inverse matrix multiplied by derivative of the initial
What
matrix.
about absolute value of determinant? What about absolute value of determinant? This formula is true if you apply it only for the matrix with a positive determinant.
For modular it's 2, right? I think.
Are you sure?
I can derive it if we have something to write.
No, we don't have. Have you
Yes, I
derived by
checked
itself?
this.
Okay.
Yes. Okay. So we use this formula, and I just write it. Change A to alpha matrix. Is this? And let's look at the terms of multiplication. First of all, we can swap trace and limit, because trace is a linear operation. And let's look at limits of this matrix and this. Limit of the first term is identical matrix, because the initial matrix tends to identical with epsilon tends to 0, so the inverse too. And the second term, when we differentiate this matrix with respect to epsilon, we get here 0, here we get our Jacobian, and here we get something that will tend to 0 with epsilon. So left only Jacobian of f. And we derived dynamics for our density. Here it is. And what it allows us to do, it allows to take some initial distribution, for example normal distribution, and continuously transform it to some more complicated distribution, like in this picture. Okay. Let's compare these two approaches. In normalizing flow, we have f, which is invertible and smooth transformation, and we have the following equation for change in the density, which consists of determinant as the main. And for continuous normalizing flow, f should be uniformly Lipschitz continuous in z and continuous in t. It's the meaning of the words enough good that was in the previous slides. These conditions get us uniqueness of the solution of ODE. Okay, and we have dynamics using which we can perform continuous transformation of our density. Okay, and here we said that we need cubic costs for computation determinant, and how much we need to compute trace. How do you think?
Linear.
Yes, at the first glance it seems to be linear, but let's look at it more carefully. Of course, if we have matrix, we just need to some diagonal elements, and it is a linear cost operation. But we also need to compute all of the terms in this sum. And in practice, computing each term costs approximately the same as computing the function, as forward pass. So we need to do d forward passes, and it may be too much. Now let's understand why this formula is.
But in this sense, you can't say that you have a d-cubed computation for the first case, because here you also need to calculate this df by the 0 dz.
Yes, we also need, but as authors of the paper said, this computation is about d. So here they need more for determinant computation.
And here we need only one computation on the left,
Yes.
and d computation on the right. Okay.
Mm-hmm. But we will compare these approaches at the end. And frankly speaking, here we need to compute this not once, but all the steps of our numerical integration here. We will compare it later.
Is it possible to solve this equation using one implicit integration?
Using what?
One implicit integration.
One implicit integration.
You need to make numerical integrations this ODE, and you can do it implicitly, and how much iterations you will need to solve it.
Authors, as I understand, authors of the paper use implicit methods, but it takes about 100 iterations in their experiments. Okay. Now we want to understand. Yes.
For one flow, we have like analytical density, and do we have one for continuous normalized flow? Because I see only what about analytical density function for one for continuous normalized flow?
Solving differential equation, solving this differential equation, we will be able to compute our density at any point z of t.
So we don't have analytical, but we need to
We don't
solver.
we don't. Yes, we don't have a formula which we can write, but we can compute density at each point. The final density at each point of z, we can compute it.
So you have to solve the differential equation to get it.
Yeah. No, we don't have analytical formula.
Yeah.
We need some solver.
Yes.
Okay.
Yes.
This is kind of approximation.
Okay. And now we want to understand why it's true. It is because of we use automatic differentiation, not analytical differentiation, but automatic, and it put some restrictions on what we can do and how fast we can do it. Now let's understand on some simple example what is automatic differential and what requirements it has. We have a vector function with two components, f1 and f2. It depends on vector z with two components z1 and z2. And imagine that we are an automatic differentiation system. We want to differentiate these equations. And the first thing we have to do is to split these complicated formulas on some parts which we know how to differentiate. So it is sum, product, and trigonometry. And now these our functions write it in the way which we know how to differentiate. And how our computational graph looks like. The first is input, it's our Z1 and Z2. The second, we compute our intermediate values A and B. And the last, we compute our output F1 and F2. Great. And now we want to differentiate it. The first way how we can do it, it's forward mode automatic differentiation. What is the idea? Let's add some fictional node to our graph, and we want to know derivatives of our functions with respect to s. The first, it's the input of our differential computational graph, which we will set manually later. It's input. After that, we know how to compute derivatives of our intermediate values A and B, and we do it using our input. And finally, we can compute derivatives of our output, because we do know how to do it, because it is a simple operations of sum and product, which our system also know how to differentiate. Very good. And now let's set S to be equal to Z1. And if we do so, this is input vector for our differential system will be equal to 1 and 0. And we pass it through our graph and get derivatives of f1 with respect to z1 and f2 with respect to z1. The same we can do for z2. We will have another input vector for our graph, and we will get derivatives of all components of our output with respect to one component of the input, z2. Okay, and what we understand from it? We can set S to any component of our input, and we will and through one pass we get derivatives of all components of the output with respect to one component of the input. So this costs the same as the forward pass. Okay. Another way to differentiate. Reverse mode automatic differentiation. Let's add let's add S at the end of our graph. And now input is here. We will set later this derivatives. And now we want to differentiate S with respect to Z1 and Z2. So this is the first step. The second step, we differentiate S with respect to A and B, just using chain rule. And finally, we differentiate S with respect to Z1 and Z2, also using chain rule. And now, let's set S to be equal to F1. Then our input vector is 1 and 0. And then, on the last step, we get derivatives of F1 with respect to Z1 and of F1 with respect to Z2. Okay, and the same thing we can do with F2. Set S to be equal to F2. then our input vector will change. And at the last step, we get derivatives of f2 with respect to all components of the z. So here we change s, we set it to f1 or f2, and by one pass to our graph, we get derivative of one component of the input with respect to all components of the output. So we need, for this computation, we need the same, approximately the same amount of operations as for forward pass. Okay. And this is all what we can do with our graph. So we understand this, that cost of computing derivatives of whole output with respect to one component of the input is approximately the same as computing derivatives of one component of the output with respect to whole input, and approximately the same as computing the f. Okay, but for computed trace, we need to separate derivatives for each component of input by a component of output. And we can use this approach, we can use this approach, but in all these ways we need d forward passes. Okay. Yes. And what we can do with it? Authors of the FFJORD invented some tricks which helps us to reduce computations of the trace. Let's see how they do it. This is we should keep in mind. And the first trick. Let's look at this multiplication. This is our Jacobian matrix, and this is some constant vector. We can swap multiplication and derivative because v doesn't depend on z. And let's look at this. This is a scalar. And as we see here, computing derivative of the scalar with respect to the whole input is the same as computing as a forward pass. So we can compute this derivative with the same cost as forward pass. Okay, this is the first trick. The second trick. Let's look at this expectation. This is some matrix, and this is random vector with zero expectation and identical covariance matrix. Let's write it as a sum. This multiplication, write it as sum. And we can change, we can swap sum and expectation. And after integration, we will get Kronecker symbol instead of epsilons. And this is exactly the trace of the matrix. Okay. And now let's use these two tricks to make computation of our density easier. First of all, this equation we know from continuous normalizing flows. And we want to compute trace. Yes, and we want to compute trace. First of all, we write it using this formula. And after that, we swap expectation and integration. And if we throw out expectation, we will get unbiased estimation for our log probability. Okay, and this is the main idea of FFJORD. And
what about the covariance of this unbiased estimate? Because we do an integration from 0 to t, and if we have even a small variance on each time step, we get a huge variance at the final stage of the algorithm, no?
They don't talk about it in the
Okay.
paper. But for integration, they fix one vector and do integration with one fixed vector.
Yes, but it seems like your first red and the blue graphs, and the other one goes somewhere outside.
We will see in experiments that this works.
Okay.
Okay, now let's compare all approaches. Normalizing flows. And here we need to compute determinants, which is cubic, and we have to do it L times because we have L transformations. Continuous normalizing flows. We need to compute trace, which costs d forward passes, and we need to do it hat L times, where hat L is number of steps in our numerical integration. And FFJORD, in which we compute this term with cost of one forward pass. After that we need to multiply it on the vector, and it is d, and after that integrate, and it is L hat. So we see that in theory FFJORD is the fastest approach, and it not require any restrictions on Jacobian of this matrix in contrast to normalizing flows, and that's why they named it free-form Jacobian of reversible dynamics. Well,
I think that the restriction is not on Jacobian. The restriction is on function f itself, because in this approach, f could be any Lipschitz function, and in normalizing flow it should be an invertible one, which is a very restrictive thing.
Yes, and moreover, if we want to reduce our computation, we put restrictions on Jacobian to be triangle.
Oh, okay.
Okay, let's look at their experiments. The first is experiment on two-dimensional toy data, and they compare with other approaches which also use flows. We go use normalizing flow, and this is continuous normalizing flow, but it is planar, and it's very poor continuous normalizing flow. And we see that the FFJORD approximate initial density better than other approaches, and it can approximate good areas with low density in contrast to below and the CNF.
And how do you learn the FFJORD using the data? You need to solve something like maximum likelihood problem.
Yes, they maximize likelihood.
For maximizing likelihood, you need a derivative of this likelihood with respect to theta. True?
Yes.
And how do they compute it? Through all these log determinants.
This is a good question, frankly speaking. I don't know exactly. but they said that they directly maximize log likelihood.
Maybe we return to the formulas for the log likelihood.
Okay.
So we need to take a derivative of this with respect to theta. And
Yes.
we know the derivative of z with respect to theta.
We know the derivative of what?
Of z,
With respect to
theta.
theta.
From our joint operators, no?
We know. Just. Let's go to. Right. Maybe I will write on the whiteboard.
Okay, let's try.
We have I'll show it today because they show it too. It is estimation. Okay. And what do we want? We want to. Так. We want this, yes? Okay. How we get it? We have our joint system.
You forgot on the expectation.
Okay.
Just fix one epsilon.
No problem. Okay. We have our adjoint system. Which is this and okay, and this is right for this ODE. Yes, and here we have another ODE in which which f is this. So for our last function, this will be the following. is parameters of f and parameters of this dynamics. Okay. And here.
And why this trace is actually f? Why this trace is actually f?
Yeah, it's not clear.
Or you introduced a different notation, f tilde, say.
Okay. F. F tilde. We solve this equation to get density at time capital T. We solve this equation using ODE solver. Yes? Okay. And we want to train it. We have parameters and our dynamics theta, which sits in F. So I think we can use our knowledge about drawing system and just write the correct terms in the place of f tilde and z. Am I right? No?
What do you mean by correct terms?
This is ODE, which we solve using ODE solver and train using the drawing pattern.
And get z and p of z of big T. Yes? And so we get z and p of z. Solving two ODEs.
Yeah, yes, okay.
And how do we estimate the gradient with respect to theta?
Okay. I think I understand what you want to say. Yes. Let's write this the whole system. Yes, we. We solved this system together. So this is a vector, and it is our f from here, and our z from here. It is log density and z. Yes. Okay. And our f tilde has parameters theta. And let's write it.
So it should be third or differential equation for estimating this gradient, no? So it should be a third differential equation.
Yes.
On this gradient.
Yes, it's here, and we just need to put instead of f tilde this vector, and instead of z, this vector.
Okay, and solve it using the
Yes,
ODE
and
solver.
solve it using ODE solver.
Okay, great.
Let's go back to experiments. This is where I talked. And other set of experiments. This is experiments on real data, real tabular data, some tabulas, and authors compare their approach, FFJORD, with our generative models based on normalizing flows, and with outer regressive models. And they, as we can see, low.
And what are the data set? What is power, guess?
It is some tables, some real tables.
Tabular data?
Yes, tabular data. And here the lower number is better. And we see that autoregressive models outperform FFJORD, but FFJORD outperform other approaches based on normalizing flows. And authors said that FFJORD is better than autoregressive models because it because we can sample from FFJORD through one forward pass, but for autoregressive models we need D-sequential computations, which may cost a lot if D is big.
And what about these epsilons? How many epsilons they use within learning of FFJORD? Only one, or?
Epsilons are for...
Yeah, for trace estimate.
For traces, they use another epsilon for each batch.
One epsilon for each batch?
Yes. And for different batches, different epsilons. And moreover, they add that FFJORD, the training FFJORD, that FFJORD is slower than other approaches, but because of because we use adjoint methods, we have more memory, and we can do our training with bigger batch.
And what about the function f? What they use in FFJORD for the function f?
Some neural net. What
Convolutional or what?
No. Here for MNIST-CFR, the first blocks was convolutional, and it wasn't in the FFJORD. It wasn't F. It was before FFJORD. And after that, they get flatten vector and pass it through FFJORD. And here, I don't remember how many layers they have here. There's something fully connected and some Lipschitz activations.
Yeah, but there should be a difference between NVP, where NVP is what?
NVP is some approach based on normalizing flows.
So, and there should be an invertible function f.
Yes.
They use quite restricted class function.
Yes, and in FFJORD we are not restricted to using an invertible function, and can
Yes.
use any neural network.
Yes.
And so do they use a more powerful network within FFJORD than in NVP? Or they use just the same transformation within both approaches?
Frankly speaking, I don't know. I don't remember, but I think they didn't write about it.
Do you have a number of parameters? Or
Number of parameters, the
how can you
architecture.
complex your functions? Yeah.
So I believe that they tend to use a smaller number of parameters because the model is much more heavier from computational point of view, and it's very hard to use a comparable number of parameters. So their parameterizations for neural networks are simpler.
Yeah, but they used a different neural networks.
Yes.
Okay. And also they add FFJORD into Bayes, and they compare with other flows, with Bayes with other flows, and with Bayes with no flow, and they get the best results in these experiments. Also, they compare with our generative models, and this column says that model can directly be trained on a data, which means it can maximize log likelihood or something like this, and normalizing ordinary. They said that ordinary normalizing flows cannot do this because it is hard to invert. It is hard to invert transformation.
Why? I didn't get it. Didn't get it.
Frankly speaking, me too. Because
I can train normalizing flows of data. Yeah, I can do it.
I don't know why they think so. Because in the paper about normalizing flows, they said that they can.
And what is the difference between real MVP, for example, and normalizing flows?
Real MVP and normalizing flows.
In normal normalizing flow, we do not have a tractable inverse. We can just compute log equivalent while we do forward pass. And real MVP flow, it has a practical reverse. You can do forward pass and reverse forward pass easily.
Okay, and one pass sampling means that we can do one forward pass and sample from distribution that we approximate. And auto-regressive model, we cannot do it through one pass. We have to conduct the sequential computations and exact log likelihood estimation. It is about this that we train on log likelihood, and in variational recordings we train on elbow, and in GAS we don't have exact log likelihood. And freeform Jacobian, it's about this, that we don't put any restrictions on the form of our Jacobian, and everywhere FFJORD is the best.
Excuse me. I think that actually you have some form of restriction for the Jacobian, because if you look at the training equation for FFJORD, you can see that when you apply the parameters, you have the integral of the trace of Jacobian. Yes. Mm-hmm. And for conventional normalizing flows, it is very difficult to keep such forms of transformations that have the Jacobian that doesn't depend on Z. Because if it depends on Z, then you have some issues. When you optimize the equation, you have the log density from for the Z0, and for example for normal distribution, which is something near the mode, and then you have some function that may depend on Z. And when you optimize such a function, this doesn't guarantee that when you will try to sample real objects by sampling from the normal distribution near the mode, then the final density may be not very high, because you may shift it because of that term that depends on Z.
Mm-hmm. And what restrictions?
This is the same case. You should ask for the trace of the Jacobian not to depend on Z, I think.
Could you repeat why dependence on Z is bad?
Well, imagine how do you sample using the normalizing flow. You sample from the normal distribution
Yes.
and transform this sample. But
Yes.
yes, and how does the density transform? It is the density from the normal distribution, and if that term or with the Jacobian depends on z, it may be shifted in some unpredictable manner.
But if Jacobian does not depend on d, then the probability of d always proportional to its probability using Gaussians.
In all the, as far as I can judge, in all the contemporary conventional normalizing flows, the Jacobians do not depend on z.
Actually, it depends on z. Because I mean, like log probability.
Let's look at the focus.
Yeah, it's log probability of z with respect to Gaussian distribution, like z0 of Gaussian distribution, and
what's the problem here? If Jacobian depends on z.
Because when you transform the density, it you don't know how it will change.
You know.
You may sample a very probable sample from the normal distribution, but
Yes.
it may become totally improbable after the transformation.
but you train your shift in such a way that it's like much your data to high data region.
It seems that we have here some guarantees from ODE solver for the P of Z. Because we take them from solving ODE and we put the epsilon there and have some guarantees from that.
Yes. Okay. And summary of my talk, we can use normalizing flows to understand how density transformed and continuous. Normalizing flows do it better than ordinary normalizing flows because we don't need to put restrictions on our Jacobian. And FFJORD do it better than they both, and we can do this transformation continuously. Yes, and this is the last slide of my presentation. If you have any question, let's discuss.
Okay. Any questions? Well, I have one. When we learn neural network, we need to do a bunch of engineering tricks on, I don't know, batch normalization, dropout regularization, everything. But here, when we approximate our neural network with this continuous time dynamics, it seems that we do nothing. We just run the ODE solver and don't bother on any problems with solving neural network. Why this is so?
Because it is not exact so. We have some problems because in theory we can solve any differential equation using ODE solver. But it is not true, and after so the paper said about it at the end of the paper, we have some problems if our differential equation is non-stiff. When we have very small and very big values in our spatial спектральном разложении, в общем. Yes, spatial decomposition, thank you. If they have very different values in our spatial decomposition, we are not able to find the optimal step of our numerical integration, and we have big problems. And we have to do, we have used some hard solvers which need much more steps in the numerical integration. So in practice we have to restrict our function and regularize it.
By what means?
By decay they use, they said.
Because it seems that we can't use ideas like dropout here, because we do not only the forward pass, but the backward pass as well within the solver. And we can't do just the forward transformation. Okay, so it seems that there are problems with this
Yes.
method as well. Okay, any more questions?
I have, how you implemented this method using Python? You need, do you implemented solvers, ODE solvers by yourself, or you used some?
They implemented solvers by themselves using PyTorch. They do that on GPU.
And and they have them in open.
They released code on GitHub.
Okay.
Okay. Let's thank the speaker for very nice talk. In a very lecture manner that you described everything within the method I use. This is very good. Thank you.